We'll go ahead and get started.
That's my stuff. I'm over it.
I'll start with any questions that you might have over the homework. So questions over the homework? Anything over the homework?
I think number 19 on page 7 is wrong in the book.
It could be. Okay, what page? 7? Page 7, number what? Number 19? Okay, let's take a look at it. So what did you get on this?
I got 8 over 35.
8 over 35?
That's the one I had a problem with.
Okay. Now remember me telling you that I'm not a big fan of this packet? Yes? Part of the reason I don't like the packet. Hello, 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 hello. I just want to make sure everyone catches this. Part of the reason I'm not a big fan of the packet is because there are a lot of errors, even in the answer key. So we're on the 5th revision of this. And so it is quite possible that that number 19 is incorrect. So I think if we work through it, we'll see. It could also be correct. Emily is buying 2/5 pounds of beans for dinner. Ricky is buying 7/4 of the amount of beans that Emily is. How many pounds of beans is Ricky buying? Express your answer in simplest form. Okay, so let's try again to see if we can't use easy numbers to make this problem make a little more sense. So let's say that Emily is buying 2 pounds of beans, all right? Emily's buying 2 pounds of beans for dinner. And Ricky is buying, I don't know, half the amount of beans that Emily's buying. Then how many pounds would Ricky be buying? 1 pound. Now, how did you get that answer?
Divided Emily's beans.
Let's try this again. What if this was 4 pounds and this was a half? How many pounds would Ricky have? 2, right? Because you're doing half of 4, right? Half of 4. Half of 4, when you use that word of in mathematics, it usually means multiplication. What you're doing here is you're taking whatever number is here and you're multiplying this number here. So like in this example, or with me changing numbers, this would be 4 times a half, which is the same as 4 over 1 times 1 over 2, which is 4 over 2. So multiplication is straight across, right? And then 4 divided by 2 is 2. Yes? So what we need to do in this problem is we need to take 2/5 and multiply it times 7/4.
Yeah, I'm wrong.
Okay, well, but you understand?
Yeah, it's just words.
Okay. So, and that I think I told you on the beginning, the thing about this class that will make it somewhat challenging is the fact that the arithmetic isn't necessarily what you're going to get hung up on. You're probably going to get hung up on word problems, which is natural. I mean, that just happens in all math classes, right? Okay, so multiply across, you get 14 over 20. And then you can reduce that fraction 7/10. Is that what the key had?
Yeah.
Yeah, okay, so that is correct. So Ricky is buying 7/10 of a pound, 7/10 of a pound of beans. Any others? Told you I don't mind going through a few problems to start class out every day.
For some reason 22, I couldn't.
Same section?
Yes.
Okay. What's going on here? 22? Oh yeah, Sheila. Yep. Sheila likes cupcakes. All right, so Sheila was making cupcakes for the school parent-student dinner. In the blender, Sheila knew that she had to put in 13 2/3 ounces of ingredients she had to mix together. After she was finished, she poured the mix into 2 1/4 ounce cupcake tins. How many of these cupcakes would one batch of this mix make? How much would be left over? Okay, so do you want to try other numbers or do you want to just stick with it? You sure? Okay, so what is the operation that you're doing? You're dividing what into what, or you could also say something by something. You're taking 13 2/3 and you're dividing it by 2 1/4. So just so we can get our language correct here, there's two ways really that you could say that. You could say you're taking 13 2/3 and dividing it by 2 1/4, or you can say you're determining how many times 2 1/4 goes into 13 2/3. All right, so there's just different ways of saying that operation. So the way that the way that I encouraged you to do this is to get everything out of these mixed number forms first. So this is equivalent to, we go 13 times 3, which is 39 plus 2 is 41 over 3, and we're dividing that by 8 9/4. And then to do division, we don't do any canceling yet, right? We don't go 3 into 9, we don't do that. We flip it over, change it from division to multiplication, leave the first one alone. So 4 over 9, like that. And then we do what? Multiply across. Okay, so if we multiply across 164 over 27. So, you know, that's the answer, right? That's how many times this goes into this. All right? But we want to know how many actual cupcakes this is. So now we want to go back to a mixed number so that we can see any whole numbers in our answer, just like this. We can see whole numbers. So we do our old school division here like this, and we try and work this out. So 27 doesn't go into 1, 27 doesn't go into 16. So you just kind of have to guess at a number here. What is it? 6, so it goes in here 6 times. Multiply 120, what is it? 162? Yes? Okay, and then subtract and you get 2 left over. So your answer is 6, I'll just put it here, 6, and then your remainder 2 over your divisor 27.
Okay, then the packet's wrong.
What did the packet have?
Then you should have 1/6 of an ounce left.
How many of these cupcakes were one batch?
They have 6 cupcakes and then 1/6 of the remainder.
No. Yeah, you have to subtract a different one because it's not. I did that when I first did it. I got 2 over 27, and then I redid it. I got 1/6.
I did it individually. So
What do you mean individually?
so I took the 13 2/3 and subtracted 2 1/4 6 times,
Yeah.
going over and over.
And then you
So taking
subtract
the
it
total
from that.
so I took 13 2/3 and subtracted 2 1/4. And that total I did it again minus another 2 1/4 all the way till I got to 6. And I had the 1/6 left over.
Okay. Here's, I think, what's getting lost in this. Look at the last question. What does it say? What does the last question say?
How much of it left over?
Okay, how much of the mix is left over, right? It's not asking you how much of a cupcake is left over. That's the part that I think everyone's kind of missing, right? So think of it this way. You had this batch of mix, right? So this is your mix. And then you start making little cupcakes out of this, right? Here's a little cupcake. I know, it's beautiful, isn't it? So there's another cupcake. You got all these little cupcakes, right? And how many of them do you have? How many can you make? 6 and 2/27. So what you have is 6 of these, right? 3. So there's 1, 2, 3, 4, 5, 6. And then you've got not enough, right, to make a whole nother cupcake. This is 2/27 of a cupcake left over. This is not 2/27 of the mix left over. Do you see the difference? You have a little bit of cupcake left over, 2/27 of a cupcake. But in terms of, they want to know how much mix is left over, right? Does that kind of make sense? We don't have the answer yet of what does the key say? 1/6. So how in the world are we going to get 1/6 from this number? What do we need to do? What's that?
Would you divide 13 2/3 by 227?
So there's multiple ways I think you could approach that. Let's try that and see what happens. I kind of like the idea of subtracting 6 of these from that. Like, who did that? And then you found how much mix was left over. You could do it that way. But let's see if we can't do it with this fraction. All right, so 2/27, and what was the suggestion? To do what?
Take 13 2/3 divided by 227.
And divide it by this? Trying to think of another way that I could help you see this.
You can multiply 2 1/4 by 6.
That's it. Okay, but how can I help you see that? Think about each of these cupcakes. Okay, how many ounces is in that cupcake? 2 1/4. How much is in this cupcake? 2 1/4. 2 1/4. 2 1/4. Okay, how many ounces are in this cupcake? Not 2/27. It's 2/27 of a 2 1/4 ounce cupcake. That's the way you can get the 1/6. Does that make sense? So what we need to do to get this final result, okay, is to take 2/27 of 2 1/4, which is the same as saying 2/27 times 9/4. I'll convert 2 1/4 over there. And then when we do this, you can either multiply across or you can simplify. This will give you the 1/6. Is that all right? Yeah, I think if you were to take that 13 2/3 and multiply it by this or divide it by this, you're going to get some huge number. It's not going to be 1/6. Okay, this is really bothering me. Can we say that's okay, or do we need to talk about that one more? You all right with it?
So would the first answer be wrong? Yes.
What first answer?
The 6 and 2/27?
That would, well, the answer to how many cupcakes this batch would make, the answer would be 6.
Oh,
Because it makes 6 full cupcakes, right?
yeah.
And then the answer, the second part there, how much of the mix would be left over would be 1/6 of an ounce would be left over. I didn't put that there, but that should be 1/6 of an ounce. Does the answer key say ounce in there?
Yes.
Okay. Yeah. Okay, that's a good question. I mean, not a good question like I like the question, but that was a good question to ask because there's a little bit going on in there. All right, anything else? Do we have anything from the section on solving equations or order of operations? I mean, there were some in there with decimals that I hadn't even really shown you an example of, so I was thinking maybe you might have some questions over that.
Sir, I didn't get number 6. I kept getting
Which
that
page?
one. Page 7. It was 7.
Page 7,
Yeah. I don't know why I kept getting that.
number 6.
The one with the whole number.
This one right here?
Yeah.
Okay, so to do this one, we are going to convert this first, right? And the 10, I'm going to rewrite 10 as 10 over 1. And then minus, now what does this turn into? 49 ninths. Like that. And then you have, two options that I showed you. One was, you get a common denominator, but the other one was that little shortcut formula. So I'll do the shortcut. It will be 9 times 10, which is 90, minus 1 times 49, which is 49, and then over 1 times 9, which is 9. Then you subtract, what's that, 41 ninths? Does that make sense? Okay. Anything else?
Is it okay to convert that to a mixed number again?
Yep, absolutely. I'll take the answer either way. Does the answer key have that as a mixed number?
I think it is.
Yeah, to me, it's going to be either way. Unless it specifically says, write your answer as a mixed number, you can do it either way. Now, normally what I would tell students in like remember there's 2 college algebra classes? Like what I would normally tell my 14 students is to just completely get away from mixed numbers completely. And it's kind of like, you know, when you're in grade school, you learn like 3 divided by 4, like, you know, that's a notation you see, right? But then later on, we just write that as 3/4. Like this is kind of lower level notation, and this is like a higher level notation. Mixed numbers are kind of the same way. Mixed numbers are kind of like lower level, and then, you know, we use these fractions as we progress through into pre-calculus, calculus, and you never see mixed numbers in calculus. It's just not there. So I thought I saw a hand go up, no? Yes?
I need help on number 19, page 11B.
Page 11, part B, number 19. Okay. I don't know, summer school is I always enjoy summer school so much more than fall and spring. And a lot of that has to do with the student population. Like, I don't know, it's like you all appear to have actually done your homework, and I just can't get my fall, spring students to do their homework. Okay, so here we go. This one right here? Okay, let me work it out above it since I don't have much room. Order of operations, so you do what's in parentheses first, right? You try and do that. We're trying to solve for x. This is a linear equation in one variable. So inside this parentheses, there's nothing I can do. I cannot combine those two together. They're not like terms. Can't combine, can't combine. So really in the parentheses, there's nothing to be done. So now I move on, and there's no exponents, right? Multiplication, division. Really, I do have multiplication. What I have is out in front of this parentheses, there's a 1. Out in front of this parentheses, this is actually a -1 being multiplied. And out in front of this parentheses, this is actually a +1 being multiplied. So these are implied multiplications. Really, at the end of the day, what I'm going to do is get rid of the parentheses. That's what I'm doing. But you can look at it as multiplication. So I can just drop these parentheses because multiplying through by a 1 does nothing, right? So my next line, I guess I'll put it right here. The next line, I'll have 7x minus 5. Now this negative that was here has to distribute through. So it has to apply to both this x and to the -4. So that should give me a -x and a +4, right? Negative times a positive would be negative, and then negative times negative would be positive. Next one, it's a 1 that goes through, so nothing changes. So again, 3x minus 8 plus 3x minus 8. And now equals 3x minus 5. So were you good up to that point? Yes? Okay. Now at this point, what we do is we look on the left side and we try and combine any like terms together. So like terms, like all the x terms, we put them together. So we have 7x's. We're going to take away 1x, right? And then we're going to add 3x's. So how many x's will we have there? What is it? 9? Did you say 9?
Yes.
Okay, so yep, these two together are 6 and then plus 3, so you get 9x, and then put your numbers together, any numbers that you can put. So what do those numbers add up to be? Negative, I thought I heard -1. So these two together are -1, right? And then take away another 8, so -9 or -9. Was that okay up to there? Yep, equals, and then 3x minus 5. Nothing on the right side yet. Yep, so we're going to subtract 3x here, subtract 3x here. And let me go ahead and do 2 steps at once. I'm going to take away 3x here to get rid of the x term here, and I'm going to get rid of this 9 by adding 9 to both sides. So I'll do that simultaneously. So there, and then there, those cancel. So we should get 6x equals 4. So that's what you got? So divide both sides by 6. X equals 2/3. Is that not what the key had?
Oh,
Okay.
no, well, it's because I messed up. I distributed instead of like actually the 6x.
So do you mind sharing where did you make your mistake?
For the, I distributed wrong, so instead of doing the negative part, I did the 7x and then to the x. I distributed, yeah.
Oh, you multiplied these. Ah, okay. All right. I see what you did. All right. That's coming. We will do that. So that minus sign there is really the indicator of you won't do that because of the minus. Okay. Okay. While we're here and while we're looking at it, what about number 20? Did you just use your calculator and just do decimals? Okay. Everyone's comfortable with that? All right. I'll just show you there is a technique to do this where you don't have to use, where you can get away from the decimals completely by multiplying both sides of the equation by a number that would essentially remove decimals. So you know how we can move decimal points over? If you take an expression and you want to move the decimal point over one position to the right, what do you have to multiply it by? 10. Right? So anytime you multiply something by 10, the decimal moves over to the right one spot. If you multiply by 100, it would move over twice, right? So what I could do is I could look at this problem and I could say, look, it'd be really nice if that decimal wasn't here. If I moved it to the right 2 places, I would have a nice number, 854, right? Here, if I move this over twice, it would be 571. Here, if I moved it over twice, what would it be? 380. This one twice would be 3,978. So essentially, I could almost do like a mental calculation here. This is actually what I'm doing. I'm taking the whole left side, multiplying by 100, take the whole right side, multiply it by 100. The effect of that is to get a new equation, 854x minus 571x plus 380x equals negative 3,978. You see? The tricky part there, just make sure that would become a 380, not a 38, right? And now you can kind of work with those maybe without a calculator, and it's just so you know, okay? All right?
Can you do 14 on that same page?
14. That looks pretty ugly. All right, this will probably be my last one. All right, yeah, that's a mess. That's a mess. All right, so let's do what's in parentheses first. Agreed? And I'll do what's in the top parentheses to start. So let me just do that on the side here. I'm going to take 1/2. I'm going to subtract 3/4. So I'll use that little formula it's not cross multiplication, it's just a formula. So 4 times 1 is 4, and then minus 2 times 3 is 6, and then over 8. And this gives me negative 2 on top and 8, and that becomes negative 1/4. So, is that all right? All right, and then I'll just rewrite the problem. So here we go. This is going to be equal to 1/3 plus, we just determined that numerator is negative 1/4 squared, and then over, and that division bar only goes to here, it doesn't go over here, negative 1/2 squared. Like that. So these parentheses that I have here are very important, right? Because I'm squaring everything in here. And we talked about that last class. If the parentheses isn't there, you're going to get a different answer. So what do you get when you take negative 1/4 times negative 1/4? Positive 1/16. So one way to think about it is you know you're going to get a positive because you're doing negative times negative. So really you just need to know what 1/4 times 1/4 is. And multiply straight across to get 1/16. Same with this one here. This is going to be negative 1/2 squared. So that's going to be a positive number. And 1/2 times 1/2 is 1/4. Is that all right? So let me just go to the next line. 1/3 plus my fraction still, and I have 1/16 and then over 1/4. I don't know if this is the first time we've seen this. I did talk last class about this idea of what we call complex fractions, where you have fractions with fractions and how important the length of the division bar is. But you could look at this right here as being 1/16 divided by 1/4, right? Isn't that the same thing? And then you could do your flipping, and if you do that, this becomes 1/16 times 4 over 1. Right? So what I like to do is I don't like to write all this down. What I like to tell my students to do in this case is that if you have a fraction divided by a fraction, what's going to happen is this fraction down here is going to flip and come up like, the 4 is going to come on top and the 1's going to stay on the bottom. So you get a 4 over a 1 multiplied. And this is no longer here. Okay, so it's like a flipping. And that's basically what happened, right? Like this is it right here. So moving ahead as we go through, if we ever see these fraction on fraction, I'm going to just remind you, okay, I'm going to flip it up and kill it off on the bottom, but this is what we're actually doing, all right? So what happens up here now? What do we have? What's this? 4 over 16, and then that reduces, doesn't it? What does 4 over 16 reduce to? 1/4. So we're at 1/3 plus 1/4. And since this went away, basically that whole thing is gone. You no longer have to worry about the division. This was 1/4, so that's where we are. And now we add two fractions, use the little formula again. So 4 plus 3 over 12, which is 7/12. All right, does that help?
Kept adding that 1/4, so it'd be like 1/8.
Oh, okay. Gotcha. All right, let's get into today's stuff, all right? But I do have, I told you with this class we have a schedule, right? But sometimes I go off on little tangents, and I thought maybe with what we're talking about, this might be something interesting. So this is just kind of random thinking here. Everyone here is familiar with the number line, right? 0, 1, 2, right? We're all familiar with the number line? Sorry, that doesn't look spaced out correctly, but all right. So what I want you to do is just for right now, think about these numbers right here between 0 and 1. And I'd like to know if anyone has a guess as to what the number is that's right next to the number 1. So like if you were standing on the number line, right, and you were the number 1, then what number is the number that would be right next to you on this side? 0.9. 0.9?
It'd be like,
Infinity?
0.9? Infinity's way out this way. Keeps going forever.
you could decimal that out.
Oh, yeah.
Oh, I see what you meant.
You could decimal that out.
So you're saying like, so 0.9, oh, with the line on top. Okay, so that right there?
Yeah, there you go, that. Yeah, because that can go on forever.
Okay. Yeah, so when you first said 0.9, I was going to argue no, because if I do 0.91, that's going to move you even closer. And if I do like 0.99, that's even closer, and then 0.999 would be even closer, right? So this seems like a good argument, 0.999 forever. Seems like that would be as close as you could ever get, because you could never really squeeze anything in between that. Do you all kind of see that? So I don't know, is 0.99 the number right next to it? Let's see. I'm going to show you. All right. See if you can follow this. All right, I'm going to define x to be 0.9 forever. I'm going to put 2 9s, even though it doesn't matter, all right? Do you all understand? I am saying to everyone in this class right now, let's let x be that, all right? X is that number. I'm curious to know what x is. Is it the number right next to 1? All right. What would happen if I multiplied this side and this side by 10. We just talked about this. This is why I thought it would be interesting to talk about. So 10 times x would be moving this decimal point over one spot, right? So wouldn't this be 9.9999 forever still? Agreed? So we were all in agreement there? All right, so now what I want you to do is just for a second, pause on this, forget the 0.999s. Let me just ask you this question. What's 10x take away an x? So if I have 10 x's and I take away 1 x, how many x's do I have? 9 x's? Agreed? But according to this, if I define x to be this, then 10 times x is this, right? So if I take 9.99, right, forever, and I subtract 0.99 forever, what do I get? I get 9, don't I? I get 9. Because it's like the tail end of this cancels out with the tail end of this, and all that's left is that 9. All right, so let's see if we can follow this. If I define x to be 0.99 forever, then 10 times x will be 9.999 forever. Algebraically, if I take 10 times something and I subtract one of them, I should get 9 of them. But if we replace those x's here with this, we get 9. That means that 9x would have to be equal to 9. Which means if 9x equals 9, then what's x? Then x would have to be 1. So it actually turns out that 0.99 forever is not the number right next to 1. 0.99 forever is 1. Yeah, okay. So now let me just tell you that there is no number closest to 1. Okay, so when you're standing on the number line, you're at the number 1, if you were to try and like take a step over to the next number, you would realize that you actually miss some numbers. You actually would miss an infinite number of numbers. It's impossible to have a number right next to another number on our real number line, which is what makes our number system so, well, yeah. There's an uncountable infinite number of numbers just even between 0 and 1. An uncountable infinite number of numbers. All right. Let's get back to the notes. Sorry. Went off on a little tangent. That was okay, right? Just want to make sure that... So can we move past the solving the linear equations? Are you ready to move on? Okay. Let's go to the next topic, which is, I believe, operations with polynomials. Is that right? I feel like I'm missing something. Yeah, operations with polynomials. So let's just make sure we all understand what a polynomial is. First of all, I'm going to define what's called a monomial. A monomial is a single term with a number and variable slash variables. It could be one variable or more variables raised to integer powers. Now, this is getting too technical. I'm not going to quiz you or anything on this stuff, but let's just look at some monomials. 3x. That's a monomial. All right? It's a number with some variable there, and that variable is raised, in this case, to the first power. That's an example of monomial. If I did negative 5x squared, that's a monomial. If I did the number 4 by itself, that is a monomial. Mono meaning single expression here. Notice that you do not see any pluses or minuses here, right? There's no addition or subtraction. Well, there's a minus here, but there's not like two things being added or subtracted. So we have monomials. Now, a polynomial Poly means what? Many, right? Poly is many. So you have basically many monomials. So if you start putting monomials together with addition and subtraction, you get a polynomial. So here's a couple of examples of this. This is, I'll put just here, many monomials. So 3x squared minus 5x plus 1. That's a polynomial. You don't have to write them in any particular order. In other words, notice in this first polynomial that I wrote down that I had a monomial here and the power on the variable was 2, right? And then my next monomial, this one, the power was 1 on the x, right? And is there even an x here? Doesn't look like there is, but there technically is an x there. It's x to the 0. You could argue that it's x to the 0 because anything to the 0 is 1. Anything to the 0 is 1, except 0 to the 0, but we're not going to talk about that. Any number other than 0 raised to the 0 is going to be 1. So notice that the powers descend. They go down, right? 2, and then 1, and then 0. We call this descending order. This is another polynomial, but it's not in descending order, right? If you put it in descending order, this would be the first one you'd write, and then this one would be the second one, and then this one would be the last one. That would be put in descending order. But it doesn't have to be, all right? The order is not important. All right, so what we're going to do is we're not going to be talking about like, hey, let's write out some polynomials. We want to do operations with polynomials. So we want to know, make sure we know how to add them. If I give you 2 polynomials, how do you add them together? If I give you 2 polynomials, how do you subtract them? And then how do you multiply them? And division, no, we're not doing division, not in here. So let's do some operations with polynomials. Oh, I should have illustrated something, sorry. Let me put one of those back. I'll just make a new one. Here we go. Okay, so each of these things are called terms. Okay? Sorry, term. That's a term, because you're going to hear me using that language. Each of these are called terms, all right? You could call them monomials, but we're going to call them terms. So terms are separated by addition and subtraction. That's what makes them a term. So what are like terms? This is some language. What does it mean to say that 2 terms are like, or that they are like terms? Okay, so to look at 2 terms and say that they are like, all you have to have is the same variable. So like, look at these 2. They both have x, right? So far, so good. But then they have to have the same exponent, or the same power. If they have the same variable raised to the same power, then they are called like terms. And if you have like terms, you can add them and subtract them. So like terms, same variable. I'm going to say variable slash variables raised to same power. Ooh. So I'm going to give you a couple of examples of like terms, or you tell me if these are like terms. How about 4x to the third, and then let me write another one over here, negative 3x to the third y. Are those like terms? Well, they have the same variable raised to the same power, right? But this one has a y and this one doesn't. So these do not qualify. They have to have the exact same variables raised to the exact same powers. Would this work? So these did not qualify, right? So that has the same variables, right? They both have x and y, but they are not exactly raised to the same power. So this one's y squared, this one's not. So these would not be like terms. These things, basically if you cut the numbers off, if you just hide the numbers, what you see needs to match exactly for them to be like terms. So no good here.
What about the order?
Order doesn't matter.
So that if it's y squared x3 and the other one's x3 y squared, it's still the same, right?
Yep. Now, why is that?
Well, they're still the same variable with the same power.
Mm-hmm. What's the operation happening between these? Multiplication. And multiplication in our mathematical system is what we call commutative, which means that you can change the order when you're multiplying. 2 times 3 is 3 times 2. Now, addition works the same way. 3 plus 2 is 2 plus 3. It does not work for subtraction. Right? 2 minus 3 is not 3 minus 2. So because multiplication is commutative, you could just flip this over, it'd be the same thing, and then they would match, right? Okay, so good question. All right, so we know what a monomial is, we know what a polynomial is, we know what a term is, we know what like terms are, and now we have the pleasure of trying to do some operations with them. So let's get to the examples. I know that a lot of you have seen this, okay, so sorry if this is too much of a grind. All right, let's look at this right here. Operations, we're going to take that and we're going to try and do the operation that is indicated. So you can look at this here as a polynomial, isn't it? What's in parentheses? Are any of these like terms? No, none of them are like terms. Over here we have another polynomial in parentheses. None of these are like terms, and we have subtraction. So we are trying to subtract 2 polynomials, and that's what we mean when we say operations with polynomials. It's either addition, subtraction, multiplication, or division. Those are our 4 arithmetic operations. So I want to subtract. So the only thing I can really do, because I can't combine these together, and I can't combine these together, is to hopefully try and drop those parentheses out. So what can I do to the parentheses on this first one, and why? Yeah, just basically multiply by 1, which is going to drop them, right? So I'm going to drop the parentheses on the first one. Nothing is going to change in here. So 3a plus 2a squared plus 3a cubed. Now on the second parentheses, it's not as simple as just dropping them because it's a minus, right? Had this been a plus, we would just drop them, wouldn't we? Because it's minus, we look at it as a -1 and we pass it through the parentheses like a distribution. Distributing multiplication through. And so that's going to give me a -a this time, a -2a squared, and a +3a cubed. You all agree with that? Okay, now we have no parentheses, so everything kind of lives in the same universe now. They're not separated or clumped together. And now what I can do is I can start combining any like terms together. So let me start underlining some like terms. This one right here, that's a like term to that one, right? So I can combine those. I take 3a and I subtract an a and I get 2a. 2a, and then let me do something different here. I'll circle this one and I'll circle this one. Those are my only ones. Those are like terms because they both have a squared. And they actually kill each other off, don't they? So that's gone. And then the last like term, I've got this one here and this one here. Those are like terms. They're both +3s, so I add them together and I get 6a cubed. That's it. Your answer is a polynomial. So you start off with 2 polynomials. You subtract them, your answer is going to be a polynomial. What about those parentheses? Just drop them on both, right? Because you have a plus here and a +1 out there, so let's just drop them. And you know what? While I drop them, and I'll just drop them. The only difference really between this problem and the previous one, aside from the fact that it doesn't have a minus here, is that we got some fractions, right? So let's start with the a's. Got that one and that one. Those two I can combine together pretty easy, right? 3a plus 6a is 9a. Okay. How about the a squareds? I've got this one, and I've got this one. So how do I combine those? I mean, when we did 3a and 6a, we said it was 9, right? So you just did 3 plus 6. Here we're going to go 2a squared minus 2/5 a squared, so you're actually going to need to do what? 2, and then you're going to need to subtract 2/5, right? And then whatever that answer is, you'll put the a squared next to it. So I'm going to go on the side over here and just do that real quick arithmetic. 2 minus 2/5. I rewrite 2 as 2 over 1. And then I do my little cross thingy again. All right? What is that when I do that? 10 minus 2 over 5, so 8/5. So we're going to get plus 8/5 a squared. Are there any questions on that part? Yes?
Question, but like towards the answers, do you care which order like the exponents are in? Like, do you want the biggest exponent or the lowest?
No, that's what I was saying earlier. A lot of people like to say, like, put it in descending order. But really, descending order is important later on. We will look at a polynomial and we'll say, hey, we're going to do something with this, but the first step is to put it in descending order. For an answer like this, it's not required because it's correct. I mean, you flip those over, it's the same expression. All right, what about the cube stuff? We've got to do this guy right here and this guy right here. So what is the little arithmetic thing I'm going to do over here on the side? 3/5 minus 3. And I'm going to go ahead and do that 3 as a 3 over 1. And then do my little thing over there. So let's see. Let's try and do it in our heads this time. This is going to be 3 take away 15. 3 minus 15 is negative 12 over 5. Negative 12/5 a cubed. And that's it, right? We took care of everything? Why don't you do number 3? Yeah. Why don't you take, I'll give you, let's say, 15 seconds. No. I'll give you about 2 or 3 minutes, see if you can get number 3. Just be careful with that minus sign. You've got to take care of that first. Anybody having trouble getting the packet or the calculator? Please have those next week. If you have a question or you're stuck, you can raise your hand. I don't mind coming and helping. I have up there what I believe the correct answer is. Anybody agree? Yeah, okay. Good, good. Who's done? Show of hands there. About half the class? Okay. Trying to get a feel for how the speed at which y'all are doing these. I'll give you just one more minute. Okay, so if you're not done, I would be a little bit, not concerned, but I would just say that you're going to need to kind of work at the speed of things, because part of the problem in a math class is when you get to that exam, like, you may know how to do it, but if it takes you 10 minutes to do that problem, like, you're never going to get through the test. And so part of a test is not only do you understand how to do it, but can you do it in a timely manner. So if you're still not done with this, just know that you need more practice to get proficient to the point where you're kind of knocking these things out quickly. So this is the answer. I won't go through the work. If you didn't get this, feel free to ask me after class. We can talk about where you might have gone wrong. Let's talk about the next one. And I thought maybe before we did that, I would just ask you a quick question about something like the problem we're about to do. And I thought I'd do it with something a little more simple. Like, what about if I say x plus 2 and I say square it like that? Then do you agree that the x plus 2 is a polynomial by itself? That's a polynomial? Okay, so we're trying to square a polynomial here. What is the most frequent incorrect answer that I get for this? This is incorrect, but it's what?
Probably x plus 2x, yeah.
X squared plus 4. That is the most incorrect answer that I get. So the student who did that, what did they do? Do you mind letting them? Yeah, all they did is they said, all right, look, I'm gonna take this squared, I'm gonna put it here, square the x, and then I'm gonna square the 2, and I get 4, and there's my answer. Now, why is that wrong? What am I supposed to do?
Multiply.
You're supposed to, okay, so I was hoping someone would say FOIL. You're supposed to do this instead. You're supposed to take x plus 2, write x plus 2 again, and this is like an implied multiplication. And this is kind of what you did on the homework where you had the little hiccup there. So there's a multiplication dot there, even though we don't write it. But this means this times this, right? And then we do this thing called FOIL. FOIL stands for what? You do the first ones, so that means you multiply the first ones together. So this is the first one in this parenthesis, this is the first one in that parenthesis. So you multiply the first ones, what's x times x? You get x squared, so we like to draw a little, there's your first one. And then you do O which is the outer ones. That means the outside ones multiplied together, which gives you plus 2x. Then you do the inner ones. These are the two inside ones multiplied together. And then finally you do the last ones, which are the two twos. So I already did that. I do that. And I get the 4, right? So the correct answer should be x squared. And then these two are like terms. Come together, become 4x, and then plus 4. All right? So just a quick show of hands. And I don't, again, we're not here to embarrass people or anything. How many of you looked at that and actually would have got to this? Yeah, a lot of you? Okay, good. Now, why? Why do you do this? Like why not this? Why not? I mean, I know you've been told this, right? But why not that?
Because that's parentheses.
Yeah, so what? I mean, what if, I mean, you've been told that if you see this, you do this times this, and then you do this FOIL. Why? Why do the FOIL? Because you were told, right? Do the FOIL? Why? What if you were told to do that and that, and then you'd be doing this, right?
Because you're not plugged it in.
So if you tried some other number in there, it wouldn't work out?
If you graphed it, it would be on 2 different places.
Graphed.
If you graphed.
Oh, you mean like graph the quadratic? Yeah, okay, now that, yeah, so we're further out now. I don't want to graph quadratic functions right now. I'm going to try and just convince you as to why it's this and not this, all right? I'm just trying to convince you of it, all right? See if I can. Before I can do it, I just want to make sure everyone agrees with me that if you have a rectangle, that we can find the area of a rectangle. If you know its length and you know its width. What's the area of a rectangle if we know its length and width? It's just length times width. Can we all be okay with that? All right, that's all I need in order to show you this, all right? So here we go. So what I'm going to do is I'm going to get this little ruler here, okay? And I'm going to measure out here. I'm going to start this dot and I'm going to measure. I'm going to do a straight line here. And I'm just going to stop somewhere and I'm going to call that x, okay? X goes from here to here. With me? That's x. And then what I'm going to do to that is I'm going to add to that a little bit more. This is actually exactly 4 inches, all right? So this is 4. So this entire side is how long? You know what? Sorry, let's do 2 here. Sorry, let's do 2 so it'll match this problem. So how long is this side? X plus 2, right? X plus 2? Agree? All right, so now what I'm going to do is I'm going to take that same x, go up like this, and that's x again, right? And I'm going to measure this out. Now I'm kind of lying to you now. This is not 4 inches. This is 2, all right? So I come up like this, measure up, and I'm going to say that that's 2. So how long is this entire side? X plus 2 again, right? What is the total area of this box that I've created? Wouldn't it be this side times this side? Yes? Isn't that x plus 2 times itself squared? Yeah? That's the total area. All right. Now what I'm going to do is I'm going to break this total area up into smaller pieces. So come out to x, I'm going to go up and over like that. So from this one over, this one down. Can you tell me the area of this one? This red box, what's the area? X times x, right? That's x squared. Can you tell me the area of this little box right here? 2. The area of that is 4, right? So check this out. X plus 2 squared, the area of the whole thing is x squared, also this 4, right? But there's more. We haven't done this, have we? And we haven't done this. So if you say that this answer is this, it's incorrect, right? All you've accounted for is this piece and that piece, right? So what are these other pieces? What's this piece in here? I'm out of colors. What's this piece in here? So how wide is it? 2. How tall is it? X. So this is 2x. How wide is this? Well, 2 and then x again. Isn't that 2x again? So your total area, this right here, needs to be equal to this, plus this, plus this, plus this, which is that right there, right?